of Batna in 1990, then moved on to acquire his MSc and PhD degree in Electrical and Computer Engineering from National Polytechnic Institute of Grenoble, France. He went on to acquire various academic accolades in the years to come. Analysis, design, and control of electric machine, variable speed drives for traction, propulsion, and renewable energy applications, and fault diagnosis of electric machines are his main interest of research and experience. Currently, he is a full professor of electrical engineering at the University of Brest. He also holds prominent positions in various institutions around the world. He is a distinguished professor and a 1000 talent expert at Shanghai Maritime University in China. Professor has been elevated as an IEEE Fellow for his contributions to diagnosis and fault-tolerant control of electric machines and drives. He is a Fellow of IET too. He is the editor-in-chief of International Journal of Energy Conversion and Applied Sciences section on electrical, electronics, and communication engineering. He is a subject editor of IET Renewable Power Generation. He is also an associate editor of IEEE Transactions on Energy Conversion. Welcome back, Professor. It's great to have you back with us today. Thank you so much for joining us. Now, before our speaker starts with the session, I'll request our director, Professor Dr. Bhavesh Kumar Chauhan, sir, to please share a few words.
And thank you, anchor of the program, Ms. Shivali Prasad. I, on behalf of the management of the Institute, our chairperson, Mrs. Alka Das, and all the faculties, in particular on behalf of IEEE Student Branch BBDNITM, I welcome Professor Mohammed Danlo Zid once again, who is a IEEE as well as IET Fellow and a senior professor at University of Brest. Sir, on personal behalf also, as well as on professional part, I welcome you for blessing us again with your address, which is on advanced signal processing technique for fault diagnosis as well as the control approaches. So I'm sure this session will also be very fruitful for all the students as well as faculty members in particular who have been working in certain advanced areas of electrical and allied branches. And I wish all the best to organizing team. I really acknowledge in particular the office bearers of IEEE Student Branch, starting with Mr. Shrikant, who is the chairperson, and the vice chairman Maruti Nandan, and treasurers and secretary of this branch. And I also appreciate HOD, that is the branch counselor also of the BBDNITM branch, Professor Rafiq Ahmed, and a senior faculty in the department, Dr. Khadim Moin Siddiqui and Professor Shabanam Kushwaha. I wish great success to this, and I once again thank Professor Mohammed Ben Zid for his sparing and interacting and collaborating with us on different advanced techniques. Thank you very much. Over to the anchor.
Thank you, sir. So without any further delay, I'll hand over to Professor Ben Bozid. Professor, would you like to share the presentation today from your end so that you are more comfortable while navigating the slides, or would you want us to present?
Up to you. Maybe it's better from you, because I'm afraid the connection shouldn't be good. Maybe it's better from you, from your side.
Oh, okay, sir. Okay, so Shrikant, would you start with the presentation, please? Thank you, sir. Over to you now.
Okay.
Just a minute. I'm just start presenting.
Okay. Thank you very much for the invitation. Thank you for the introduction. I'm really sorry for the delay because of some connection problem. I am now in my office, back to my office, so hope now everything will be okay for the presentation. So while the presentation is started, I would like just to remind that this is the second part of my my presentation. Okay, the first part was dealing with fault diagnosis of electrical mechanical system, and now and the second part will deal with fault resilient control. of electrical mechanical system, and this time I will share some experiences on a specific topics, which is marine renewable energy, and I show some case studies on tidal stream turbines. Next slide, please. So now the introduction, I will reintroduce the problem now. Fault detection and diagnosis topic has been already addressed in my previous webinar, and now I will deal with fault resilience. I will give some basic concepts. So then I will talk about resilient control strategies, mainly two, and I will talk about resilient systems. I will give some definitions, and I will finally present some case studies with tidal stream turbine resilient control. Next slide, please. So for those who attended my last webinar, so the first part, fault detection and fault resilient controls is a whole part. The two topics are interacting. So the first step was detecting failures, then diagnosing this. This is almost done by a software base. So we measurements, then we deal with signal processing, then we detect fault, we localize them, and now this is the second step. So if the failure is not catastrophic, so we can decide, and this is really a hot topic. Actually, we can decide to make the system more fault tolerant. So and a new keyword is to say this is a fault resilient system. So in this case, when we have localized the fault, so and then we isolate the fault, so now we go through what we call reconfiguration. This reconfiguration could be sometimes by software and sometimes also in hardware reconfiguration. Next slide, please. So this is also a slide I have already presented in my last webinar. So this is just to show you the exact localizations of the two key topic, FDI, which is fault detection and isolations. So and then now we go through the resilient or fault tolerant control, and in this case you can find three main keywords. What we target now is change the operation or reconfiguration. These are the two main fault tolerant control approaches, and of course we want to avoid maintenance, because when we detect a fault and if this fault is catastrophic, no, we need to stop the system. So we will deal with the problem of for example, if we have a generating system, so we will deal with the problem of unavailability of energy. So the objective of resilience is to try to avoid this and try to delay the maintenance operation as far as possible. Okay, next slide, please. So what are the basic concepts of fault resilience? So if I want to give a clear definition, what is a resilient or fault tolerant system? So it is a system which has the built-in capability to continue or to a correct execution of what it was scheduled to do. So the scheduled operations. So and this is a built-in capability to operate in presence of a certain set of operational faults. Of course, by a set of operational faults means that, of course, this is does not include, catastrophic faults. So in this case, when we talk about basic concepts of fault resilience, we have two types of fault tolerant or resilient approach. The first one is what we call a passive fault tolerant control. In this case, we have a fixed, robust structure of the controller. So this control will not be changed. And in this case, in the case of passive FTC, so the faults have been already considered at the control design stage. So, and I will later say that this is not the best option. What is widely used is, of course, active FTC. And in this case, we have an explicit fault detection and diagnosis scheme. So this is clearly connected to my first webinar. So we have a fault detection and diagnosis system operating in parallel to the active FTC, which is not the case of passive FTC, because faults have been already in the considered in the design stage. And these are the two, and practically and in real world, the active FTC is the best option. Next slide, please. Okay, so if I want to get to give now some features and limitation of the two approach in terms of passive FTC, this is mainly very simple to implement, but unfortunately, it is difficult to account for a large number of fault scenarios. So if I take, for example, the case of electric machines, we will consider some really typical fault like bearing faults, like broken bar faults for the case of an induction machine and so on. But unfortunately, and this is the main drawback of passive FTC, this approach is unable to deal with unforeseen faults. Okay. Now, what about active FTC? This is contrary to the passive FTC. It has the potential to deal with a large number of fault scenarios. Of course, it can deal also with some unforeseen faults. I would like to remember what I already said in my previous slide, that this active when we design this FTC, I mean active one, so we need to consider some faults, even a large number of faults in the design stage. So, but what is the main advantage is that we can deal with some faults that have been not considered in the design stage. Unfortunately, of course, it is a little bit more complex to implement. And what is the real challenge here? In both passive and active FTC, it's the real-time decision making. Okay, thanks. Next slide, please. So if I want to give, a basic configuration of the fault resilient systems, including, of course, fault detection, it is better to divide the system in different parts. So this is the case of mainly all the systems. So we have controller. So the big systems, mainly if I will later consider specifically electromechanical system, electric machines. So we can, divide the system in three main parts: the actuators, the system itself, and the sensor. And what about faults? And this is important things to consider. So we can have faults in every part of the electromechanical systems. We can have faults in the system itself, in the actuators, and unfortunately, we can have faults in the sensing system, in the sensor themselves. Okay, and this is a big challenge when we deal fault resilience. So this means that if you want to design fault resilience, we have to design also as a first stage the fault detection system, and this system should detect fault on this part. Okay, so we have a condition monitoring system. These condition monitors will, of course, will be designed under different approach. Here, if you look at this slide, this is a model-based approach. So we can have information about the different faults, and regarding this condition, we have to decide. And as I said in my previous slide, decision making is this challenge here. We have to decide to stop the system if we are dealing with a really catastrophic scenario, or if not, we have to reconfigure the controller. So this is why we talk about fault tolerant control. Okay, in this case, when we talk about reconfiguration, we have two options, and I will later show you what are the consequences of these two choices. The first one is to consider just making the system continuing its operation, or we can also try to optimize the reconfiguration. Okay, next slide, please. So in this slide, I'm showing the two main resilient control strategies. The first one is dealing with reconfigurations. This is typically the most comprehensive action against the fault. In this case, we have two options. We can carry out a software reconfiguration in terms of control, or sometimes in some critical systems or plant, we need to deal with a material or hardware reconfiguration. So in this case, when we carry out hardware configurations, we should exploit what we call redundancy. We have some redundancy that can be inherent to the process, but we can also schedule this redundancy. And if redundancy, of course, is a cost, will induce extra cost. And in this case, the best option is to schedule what we call analytical redundancy. And in this case, the analytical redundancy will allow the reconstruction of some mismeasurement. In this case, in the case of faulty sensors, this is very, very important. And when we deal with this analytical redundancy, we consider what we call analytical models. Typically, for those who are familiar with control, if you consider sensorless control, in this case, the mechanical sensor is replaced by analytical sensors. So in this case, redundancy could be considered not only in the sensor case, but also in the actuator case or in the process hardware also. And of course, this will induce extra cost. The second possibility is the change of operations, of controller reconfiguration. And typically, this is what I will try to present you in the case studies. So in this case, the controller can be reconfigured. So typically, its parameter or structure can be changed. So this means that in the design stage, the controller should have the ability to be online changed. And this type of reconfiguration or operation of control reconfiguration must be combined with some analytical hardware redundancy. And this will allow to accommodate more than one faults, of course. Next slide, please. So this is an illustration of the two approach. If I consider reconfiguration, if you look at the first figure, the up figure, then you can see that in this case, I'm now trying to illustrating the resilient approach or the fault tolerant approach with tidal stream turbines. Which is a typical application, particularly deployed here in my region, in Bretagne region in France. So when we consider reconfigurations here, we need to do sort of hierarchy of control. So what I am illustrating here, and I'm taking in the first figure, the up figure, I'm considering, for example, a fault in the speed, in the sensor speed or speed sensor. So in this case, from the top, in the top level, we can consider, for example, a classical vector control technique of the electric machine of the generators. In this case, we need speed sensor, voltage sensor, current sensors. And if we detect a fault, for example, if we detect that we have no information about the speed, so we need to switch to the second controller, which is a sensor control. So no need. So in this case, the speed sensor is replaced by an analytical one. Okay, typically it can be a speed observer based on, for example, extended Kalman filter and Leonberger observer and so on. Now we can consider also some worst case. For example, we can lose current sensors, voltage sensors. So we have no sensor, we have no information, feedback about the data, the main parameters of the process here at idle stream. There be no information about the speed, no information of the current of the volt. So we switch to the last control possibility, which is an open loop. Here, the objective is to maintain the system operating. For example, in this is a system generating electricity. So we want to delay as much as possible the maintenance operation. And what it is important to mention here, that we need to also to design what we call a control strategy decision. So in this block, so this block is connected to the fault detections. When we detect a fault, we need to decide at what time we have to switch from one controller to another one. And in my opinion, this is a very interesting approach. Unfortunately, it needs an important pre-design stage. So we need to choose all the possible controller. We need to design a transition systems which is related to the switch. And unfortunately, as already said, the problem here is if you have an unforeseen faults, this FTC will not be as efficient as expected. The second possibility is the control reconfiguration. In this case, we have one controller. This controller is called a nominal controller, and this approach need to have what we call an internal model. So we need to compare online the internal model with some parameter of the system, and when a fault is detected, we need to readapt the reference. If you see on the bottom figures, we have an input which is reference. This reference, of course, when we control an electric machine, for example, we of course have a speed reference, a current reference, and so on. So if there is a fault, we need to change this reference online with, of course, some constraint. For example, a constraint of optimizing the energy and so on. Okay, these are the two options. One option is with the design of different controller, and we need to switch from one controller to another one. And the second option is one controller, but with its parameter readapted online. Next slide, please. So before discussing the case studies, I want now to talk about what we call redundancy. So we have the possibility, of course, when it is the case when the system is critical. For example, I take the examples of a nuclear power plant. In this case, the cost is not a problem. Security is, of course, is the main concern here, and in this case we use what we call static redundancy. So in this slide we can see that in addition to the redundancy, we have, of course, a minimum of redundancy. I'm illustrating this in terms of sensors, so we can also illustrate it in terms of actuators and so on. In this case, I'm talking about the critical case of sensors. So we need to have a minimum of sensor. This number is of course is defined regarding the number of faults, though the minimum number is 2 by n plus 1. So if we have, for example, we are dealing with problems with the speed sensor, so we need in this case three redundant speed sensors. So this is what we call a material or hardware redundancy. So we have 3 sensors operating in parallel. This is an important constraint. So the problem in this case is that we have 3 information and we need to choose what is the best one. So to the redundancy, we need to add important things here is the voting algorithm. This is very, very important. So the voting algorithm will decide what is the most the most, in fact, efficient and the most reliable information. So sometimes we can have some failures of a temporary phase in one sensors, and this voting algorithm, this voter block, will allow us to choose the best or the most reliable information. Next slide, please. Now, this is static redundancy. So we have also dynamic redundancy. So we have dynamic redundancy. This is typically used really in real-world systems and typically in power plants. So this is not the case for a quite simple systems. A wind turbine or tidal turbine is not, of course, a simple system, but this is not used. But what is the main advantage of this dynamic redundancy is, of course, the number of redundant system, redundant sensor in this case, because this number of sensor here working in parallel is reduced. For example, if we are dealing with 1/4, we do not need 3 redundant sensors, but just one operating in parallel. Next slide, please. So now, of course, when we are dealing with less critical system, if we take the example of a wind turbine, so in this case, redundancy, hardware redundancy, is a costly operation. So we need to decrease the cost, and what is target in this case is to deal with analytical redundancy. As illustrated in this slide, sometimes we can have, for example, two sensors, two real sensors, and the third one is an analytical sensors. For example, if we consider speed sensors, so we can have 2 real sensors and the third redundant sensors in analytical one. And in this case, the speed sensors information is reconstructed from the if we are dealing with electric machine, we reconstruct this information by using the current and the voltage. Of course, in any electric systems, electromechanic system, current and voltage sensors are already embedded. So these two informations could be used, for example, to reconstruct the speed sensor. In this illustration, I am reconstructing just one speed. Of course, I can consider redundant systems with one encoder, for example, in terms of speed, and two analytical informations, analytical sensors. For example, one sensors reconstructed using extended Kalman filters, and another one reconstruct using, for example, sliding mode observer and so on. We have already done this, for example, with electric vehicle. Okay, next slide. So now the topic of my presentation is fault resilient control, but we have to know that for some critical application, I'm illustrating this for airplanes, for example, the resilience is considered in the design stage, and sometimes the electric machine is designed to be resilient. For example, in this slide, I'm showing the case of a surface-mounted PM AC motors. This motor is type of this small motor which is used as for aircraft fuel pump motor. So this is a very critical component in an aircraft. So this system, this machine should not deal with faults. And in this case, this machine is not a classical one. It is a 4-phase. So typically, one phase we have one redundant phase. It is a standard. It is a waiting phase. If we have a fault, if we are dealing with a fault in one phase, we will reintroduce this waiting phase in operations. So of course, the system can machine can operate with 3 phases. It's classical 3-phase machine, but one phase is in a waiting stage. Of course, we can lose two-phase, the machine will still operate, but at very degraded conditions. So this type of system, of course, is considered, is made resilient in the design stage. Next slide, please. Another illustration is, for example, the landing systems of an airplane. This is an illustration from an Airbus A380 380 airplane from Airbus. So in this landing system, you understand that this is a very critical part of the airplane. We have two redundant systems. The first redundant system is the winding. So we have a dual three-phase configurations. Dual, by dual I mean a three-phase systems, redundant three-phase system, and also a redundant inverter. So if one of these component is faulty, is detected faulty, we will switch to the redundant three-phase system, or we will switch to the redundant inverter. Next slide, please. So another examples of physical reconfiguration. This is, of course, now I would just to remind you that we have a fault detection and diagnosis systems operating online. So when we detect a fault, for example, in one of the switch of the inverter feeding the electric machines, when we detect this, we need to reconfigure the inverter to allow the machine to continue operating. This case is a possibility. This possibility, so we have in the left side for this is the pre-fault configuration. So we have an inverter with 6 switch, and in this case, this configuration is designed to be fault tolerant. So which is very specific here, as that we have a DC bus with a midpoint. So this is not really typical DC bus or midpoint, but if you want to let this system to be fault resilient, so you need to design this DC bus voltage. We need also to add additional component like here. This is the triac and also the fast acting fuse. So if we detect, if we lose one of the IGBTs, so we have the possibilities according to the midpoint to reconfigure the system and to connect the loosed arm to the midpoint of the DC link, okay, using the triac that has been used in the design stage. Next slide, please. So this is another options, and again, this is another possibilities using a classical DC link. So if you look at the DC link, this is a classical one, but what is specific to this fault resilient configuration is that we have an additional arm. So we have a 3-phase inverter, but we have a redundant arm, so 2 additional IGBTs. If you lose one, we switch this arm into the systems. The main constraint here to allow this system to be fault tolerant, if you look at the figure and the right side figure, you can see that the safe and redundant access be connected using the possibility, the accessibility of the neutral point. And this is, of course, not a classical thing. All the electric machines are actually designed and manufactured have no access to the neutral. But this is a possibility. Here in our lab, we have such kind of possibilities. So we need to choose a specific machine, and in this case, we can have more than one redundant arms. Of course, the redundancy will induce extra costs. Next slide, please. So now I'm not maybe I can people can ask question at my end of presentation. or up to you. You can ask question. I will continue. If you have question, maybe you can stop me, or I can answer the question later. So now I will try to illustrate this resilience, or the resilient control approach with specific cases. These cases are specific to this coast side of France, the Bretagne regions. So we have very interesting marine sea to deploy what we call tidal stream turbine. If I want to summarize summarize the operation of these systems, I have take here the typical systems which look like a wind turbine, but a wind turbine that will be immersed into the sea. Okay, so for the person who are interested by such kind of system, do not hesitate to ask me later papers about this kind of system. So typically here, I will present different case study. The first case is the tidal stream systems using multi-phase permanent magnet generators. So this type of systems, I hope you understand that this type of system are immersed into the sea. So maintenance is very critical issue. And of course, we need to avoid maintenance as much as possible. I'm giving you an example of this, of the tidal turbine illustrated in this slide. In the design state, the maintenance is scheduled after 5 years. So we are supposing the system to continue operating for 5 years, because the operation and maintenance costs are very high. So we need to decrease this cost if we want to deploy more than one system. So the use of multi-phase PM machine is very interesting, and I will show you why. So I have already discussed the issue of seat intervention. We need to minimize the intervention. Of course, this will lead to minimize the maintenance, and the multi-phase PM generator is a very interesting candidate. Why? Because we have the first interesting thing that we have in multi-phase machines, we have additional degree of freedom. This degree of freedom are due to the number of phase more than three. So under faults, we can consider using the two remaining because if you are consider, for example, a 5-phase machine, we have 2 additional phase that can be used in case of fault. Next slide, please. So in this case, I will show you how we will consider controlling this type of system. As for wind turbine systems, and if you consider the system operating in the between two speed here, we are considering tidal speed between the starting speed and the speed corresponding to the nominal power. In this case, it is recommended to operate the systems in the with MPPT. So I hope that all of you know what is MPPT, the maximum power point tracking. So this is classical variable speed control. And in this case, we have a speed external loop associated to an internal torque. Of course, this is the current control. And what we are trying to do here is to when we try to control such kind of system, we want to extract as much as possible power. Okay, this is due to MPPT. And when we are dealing with faults, what we are trying to do, this is a good option, is we are trying to improve efficiency. Sometimes when the systems handles faults, these faults generally as a consequence will lead to increase the current, the electric current. So when we talk about current increase, the consequence, the immediate consequence is the increase of copper losses. So in resilient control, in this case, we will consider also the efficiency optimization, and I will show you what could be the consequences. So to carry out, to consider resilient control, we have already considered, we have also done this for wind turbine. We consider what we call high order sliding mode. I'm giving you some references of this control. Very simple, easy to implement controller. These controllers are well adapted for fault mode because these controllers are robust controllers. So no need to design this controller for a specific fault. You design it at an early stage, and this controller will operate in both case, in healthy case or in faulty case. So regarding my introduction, the approach is here is this control reconfigurations. So we have one controller which is expected to be efficient in all the operation mode. Next slide, please. We not have enough time to discuss the control, but you have the references. If I need, I can send you the papers, of course. So in this case, and this is for the real used machine tidal trim, we use a 5-phase machine. Of course, we can use a 7-phase and more. Of course, this is not really an interesting option. 5-phase is the best option. So this 5-phase machine will be used in a normal operation at a 3-phase one, and if we have a faulty mode, we will switch one of the remaining healthy phase in operation. So under the faulty condition, the remaining healthy phase can be used to compensate the faults. But of course, this is not an easy task because we need to check the system balance. So we have a balanced 3-phase system, and we switch from the healthy to the faulty mode. We need to check that the new 3-phase system is still balanced. So the transition from a faulty is not a so easy operation. So it takes some times, and these times we need to, of course, reduce it. And during these times, we can have a very big transit. So we need to smooth this transit. Next slide, please. So this is the block diagram of the control systems. So the input, of course, so is the measured tidal speed. We have two options here. We can have, of course, we have tidal stream turbine. All the installed turbines are equipped with tidal stream sensors. We can lose, of course, this information, so we can also reconstruct it. The second block is the system itself. So I would like to remind you, in contrary to a wind turbine, we have a hydrodynamic modeling here to consider. Of course, we can have a gearbox. The electric machine itself, in this case, it's a 5-phase machine. We need to control the 5-phase machine and the tidal stream turbine. We are mainly considering MPPT. So here MPPT, so we need to extract the maximum power. Of course, if the current speed exceeds the nominal one, we need to do a power limitation, of course. Next slide, please. And these are some of the results. In this slide, I'm showing you these are real measured tidal speed, which is very interesting to know here. That's you have spring tide and nip tide. So we have, if you look at the speed right in the left side, data, real data. So which is interesting here. So we have positive and negative speed, because of course when we are dealing with a tidal stream, the stream have two directions, and we harvest the power in the two directions. So of course the machine will rotate in the same direction. So these are real data, I would like to mention that if we compare tidal system to wind systems, we have a minimum speed for which the system will start to, and the tidal will start to turn. The minimum speed is 1 meter per second. Less than 1 meter, the system cannot turn. This is a constraint in the choice of the seat. So what I'm showing here is the speed itself. So now it is positive because we will use it like this, and we will harvest the power in the two directions, both direction of this speed. This speed illustrates the phenomenon itself. We have two phenomena here. The turbulence here are due to the swell effect. So if the sea surface is calm, so this turbulence will be removed. If you have sort of wave effect on the sea surface, this will be reflected on the speed. Next slide. Of course, here the data are in second, but because this is for simulation and emulation, but in real world we have a cycle of 24 hours. So what I'm showing you here is the performance of the resilient control. We have the rotor speed, and we have the rotor speed for the healthy and the faulty mode. What we can see here, that the system is fully resilient now in terms of rotor speed. So even the speed, the fault here is the lose of one phase. So if you lose one phase, we will switch from 5 to 3 phase. So initial stage, the system is operating as a 5-phase machine, and if we lose one phase, so if you want to continue to operation, we need to switch to a 3-phase system. So in this case, if you look at the results, the systems is quite robust. Though in terms of control, we are still following the reference speed. Next slides, please. Now this is the torque. So what we want to target, and this is an important features of fault tolerant or fault resilient system, is that the fault tolerance should not induce extra stress on the system shaft. If you look at the torque before and after, we have no extra. Of course, we have the turbulence. This is due to the turbulence of the tidal speed. We have no extra torque fluctuations. Next slide, please. Of course, we need to check if we the generated power. You can check the slide here, the results before and after healthy and faulty modes. Here I'm considering an open circuit, so that we again the same fault. We lose a phase when we switch from 5 to 3 phase. Again, if you compute the mean power, we will find that it is exactly the same. Remember here that we are optimizing the fault resilience. So we want that the system, even in the faulty case, still generating the optimal power. Of course, this will have a consequence. Please, next slide. If you look now on the results, of course, we need to check the current. If we look at the current from the healthy mode to the faulty mode, you can see, of course, that, of course, if you look at the zoom, one of the current, of course, is 0 because we lose a phase. So the consequence of trying to optimize the power is that we have an increase, of course, of the current. This increase is about 1.5. So there is an option that has been already considered, for example, by some tidal stream turbine manufacturer in France. We can, of course, as shown in my in one of my previous slides regarding the fuel pump, we can oversize the machine. So this is considered in the design stage. When you oversize the machine, we will have no problem of heating and so on. So this machine, of course, in the healthy case, it is oversized, but if we are dealing with such current, typically for this type of systems, if you have an open phase, though the current will increase, but with your machine will safely operate continuously with this fault because it has been already oversized in the design stage. Next slide, please. So the second case study is to show you that in the first slide we have considered a typical control method. This method, the high sliding, the previous method, I want just to strengthen this. It looks like very complicated, but it is as easy as PI control in terms of implementation, in addition to be efficient and robust. So for those who are interested by such kind of control, do not be afraid about this. It's mathematical complexity. It is very easy to implement. Now, because we are mainly talking about control, I am proposing a second case study. We have considered also, we are considered also by experiment actually in France, is the use of another type of control, typically model predictive control. I would like just to mention one important thing. If you want to compare tidal stream to wind, so the two systems, wind turbine and tidal stream turbine, one of the drawback of wind turbine in terms of generated power is that the power is connected, is stochastic, fluctuant due to the wind, which is not the case for the tidal stream. This tidal stream and this speed, as shown here, I am showing again the speed. This speed is really predictable. So we can predict it for 1 month and years and years. So this is important. So if the resource is predictable, so the power is predictable. And this is very important if you want to inject this power into the grid. So regarding this predictability, of course, model predictive control is also a very good option. So we have a good horizon of predictability. So this is the tested system. We have, again, a 5-phase machine. So when we use 5-phase machine, we need to use a specific, of course, inverter. We have here a 5-phase inverters. I'm illustrating you how the system is situated in the small figure. So we have the sea surface, and we have some data about the tidal stream system is put on the seabed, and the sea surface behavior will impact the power. If you have a calm sea surface, so we have a less turbulent speed. If it is, of course, if you have waves and swell, this will impact the speed, and of course the generated power. Next slide, please. And in this case, we use what we call a finite control set model predictive control. So we have already tested. So when we design this control, we have, of course, a pre-design. So we have a number of possible set to define according to the possible set of faults. So of course, we need to consider the set of faults before. One of the main drawbacks, as already said, that for some unforeseen faults, the system may not be as efficient as expected. So here, in terms of the resilient control scheme, is shown in the right side figures, we will still consider the optimization. So we will consider minimizing the copper losses, and we will see the consequence now using such kind of model predictive control. Next slide, please. I'm trying to illustrate this in terms of, so we use 5-phase, and we will consider different kind of faults progressive faults from one missed phase until really missing two phase. This should be the maximum. Of course, we can lose, of course, 3, but in some cases here the consequences could be catastrophic. So we need to stop the system. So in this case, we have considered different cases. The important cases is the impact of adjacent or non-adjacent phases. The problem here is the balance of the system. Remember what I have already said. So if we switch from a 5 to 4 and 3, when you need to check that the system is still balanced. So if you look on the consequence here in the rotor speed, you can see, of course, we have the worst cases. We have in black here, we have in black dashed, we have the reference. So we are, for some cases, the less worst cases, we are still following the reference speed. Of course, for the worst case, the objective is to continue operate, not trying to follow the reference speed. Next slide, please. So here we are considering the torque. We need to check always two important, maybe we have 3 parameters to check: the speed, the torque, the generated power, and of course the current. The torque is important to check. You need to check that you are not inducing extra constant, because this will lead to a fatigue of the torque of the machine, the shaft, and maybe will decrease its remaining useful life. Of course, if you look here, we have a typical case where we have no torque. Of course, this is the worst case, 2 opposite loose phase. When you lose this phase, of course, we have no torque, and we will see that we will have no generated powers. Next slide, please. And this is the current. You can look at the current. Of course, if we add the constant of power optimization, the consequence, if you look at the current, we have an increase in the current. So the 2 possibilities: if you want to have a safe operation with a classical machine, you need, of course, not to consider power optimization. Just let the system remain operating. If you want to optimize the efficiency, you need to oversize the machine. Next slide, please. This is my, I have just 2 remaining cases, this one and the next one, and this will end my presentation. Now, in the previous slide, I was in the case, I was considering faults, internal faults. And now we are considering, faults coming from the grid, because we are considering system connected to the grid. So now I'm considering what we call resilience versus grid faults. And the word used for wind turbine is the low voltage right through. So sometimes we have some decrease in the voltage coming from the grid. This is the reference taken by the machine. If this voltage decrease, the systems will follow this decrease and try to adapt. If the speed, the voltage will decrease, unfortunately the current will increase, and this should be clearly taken into consideration. And the objective is to be resilient to this fault, and also trying to inject smooth power to the grid. Next slide, please. So here I'm in fact considering two possibilities: to the resiliency versus grid faults, and also to use specific system that will have two goals. The systems here, namely, is the supercapacitor. Supercapacitor will help the system to accommodate the fault, the current increase due to fault, but also allow the power, allow to smooth the power before injecting it. Just remind you that we have turbulences, and these turbulences should be smooth before injecting the power to the grid. Next slide, please. So this is the two cases illustrating first what is the effect of supercapacitor. If you look at the systems, if you have no capacitor, of course we have fluctuations. This is a fluctuation to the nature of the tidal speed. So if we want to remove these fluctuations, we have already tested experimentally, we can use supercapacitor, and you have the red figure, yes, with supercapacitor, and we are smoothing. Of course, we have fluctuation. These fluctuations is, of course, cannot be removed. Next slide. These are experimental results. So what about now throttle speed? Of course, we are considering here force coming from the grid, and we consider really worst case. Here we are voltage sag from 5 to 10 seconds, and voltage interruptions from 5 to 5.3 second duration. And this time, and this are 2 times longer than the grid codes. I hear talking about the grid codes requirements. And if you look at the rotor speed, we have we have a robust system in terms of speed. So the speed is clearly and remains following the reference, even if we have voltage interruption. Next slide, please. Of course, now if you look at the power, so of course, when we lose half of the 50% of the voltage, the objective, this is important to be reminded that we want the system to continue operate. If you lose half of the voltage, we'll of course lose half of the power. This is the green line. So in this case, between 5 to 10 seconds, we lose 50% of the voltage. So the system continue operating, but of course generate less power. And between 5 to 5.3 seconds, we lose voltage. Of course, in this case, we have no power production. Next slide, please. This is my last study case. This is an important case. This case has been and study has been carried out by a specific manufacturer of tidal speed. They have recently discovered that because they use permanent magnet machines, very interesting in this case because of the efficiency and so on, they have experienced some specific faults with the magnets. So in this case, I will show you resiliency versus the magnet failures. We are considering really specific permanent magnet synchronous machine. This is a 3-phase, so this is a classical one, and in this case, I will show you how to handle this magnet failure. Next slide, please. Oh, this is a classical, PI control structures. Just to mention here that actual manufacturer consider a direct drive option for their machine because of the in the objective to decrease the maintenance cost. So we have a direct drive machines. In this case, the machine is rotating at the same speed that the turbine. Okay, though this is a classical PI controller. We have 2 loop, speed loop and current loop. So if you consider such kind of classical control, and if the machine is experiencing magnet failure, next slide, please. If we consider a classical PI controller, we will see later in the results that this kind of classical controller, even if they are optimized and their gains fully optimized, they are fully optimized for one type of operation, is the healthy operation. So with the classical control, the failure case will never be considered. In this case, we need to use a control that is able to handle all the possibilities. The best option is again high order sliding mode, typically the second order, because this is a robust control that can operate in both healthy and faulty modes. So this is the structures and of the control, the resilient control. Next slide. So these are the results. So we have considered, of course, typical case with a percentage of demagnetization. We can consider, of course, even the loss of a permanent magnet. So if you compare, so here in green, this is the speed, of course, the rotor speed. So we have again the same waveform of the rotor speed corresponding to the tidal speed. So of course, in green, we have the reference, and we have in dashed red, this is the PI controller, and if we consider the second order sliding mode, we will see that we have a very good, even very interesting performance. Next slide, please. This is, as I already said, second important parameter to check. This is the torque. And if you look at the torque, you can see that if you use a classical control, we'll have extra induced torque. And this should be avoided, because this will increase the fatigue of the generator. And we can see that the best option is still the high order sliding mode. Next slide, please. This is the power. Of course, same tendency here. The best option is still the second order sliding mode in terms of resilient approach. I'm showing you here just an illustration with 5% of demagnetization. If you go through the reference that is shown here, we can go up to 15% demagnetization loss, but unfortunately this is really a worst case. We have not yet tested it in experiments. Okay, next slide, please. So this and my talk, I hope I have not take much time. I hope also that you all find it very interesting. Again, I'm ready to interact with you before the end of this webinar, and you have my email, my contacts. You can ask me more detailed. We can have a detailed discussion later, and you can ask me for papers that have been referenced in my presentation. Thank you again for your invitation, and thank you for your attention. And I'm ready to discuss with you, to answer questions.
Thank you very much, sir. We have two questions.
Okay.
First question is, what will be a cost of
sorry, but I do not heard your question.
So the question is, what will be the cost of reconfigurations compared to the maintenance cost?
Oh, yes. So if I consider, actually this reconfiguration in terms of industrial deployment, so of course these are studied under, they are carried out with two manufacturers here in France. So I'm giving you an example. So actually if you have a look on my last case study, this is a tidal turbine that has been designed to operate fully under sea for 1 year, almost 1 year, with no maintenance. So the manufacturer is, of course, considering that the system will be robust for 1 year. For 1 year. So if you consider maintenance for this kind of machine, I'm giving you prices. The prices, maybe the cost, maybe will look like very high because we have no big deployment. This machine, the cost of this 1.5 megawatt machine cost is 30 million euro. 30 million euro, and maintenance cost after 1 year is expected to be almost 500,000 euro after 1 year. So after proposing the reconfiguration possibilities with different fault scenario, the new expected maintenance and seat intervention move from 1 to 5 years. Okay, so if you want just to give a price of the decrease of the cost, the cost is 500,000 euro every year in terms of maintenance. So if you move to 5 years, so the decrease is very, very important.
Is there any other questions?
I'm looking at the chat.
Sakshi, over to you.
Hello.
Okay, thank you, Shri.
Hello.
Hello, please ask your question.
Yes, sir.
Yes, sir.
Sir,
Yes.
I have another question.
Yes.
If somebody is diagnoses faults by using software, any software, means MATLAB or any other software is diagnosing bearing fault, broken rotator bar fault, air gap eccentricity fault. So what is your view of software-based condition monitoring of AC machines?
Oh yes, you know, this was presented in my first webinar. So yes, actually all the deployed systems are software based. So of course, when we try to design method, we start by classical system like MATLAB and so on. But you know, if you look at the industry actually and the deployed system, all these diagnosis systems are software based. But I would like to mention that the, research development are using classical software like MATLAB, but actually we have removed. So now we have moved from deploying techniques on MATLAB, and we prefer deploying techniques on open source like Python development. But this is better. But anyway, all the systems are software based. The detection are software based.
Thank you very much, sir. Your
Thank you, sir.
valuable answer. So, any more question from the audience? Okay, Shrikant, go ahead. I think we have discussed all the questions.
Sakshi.
Yeah, thank you, Srikant. I, Sakshi Priyam, Treasurer of BBDNITM Student Branch, Lucknow, obligingly extend my abundant thanks on behalf of the institution to Honorable Mohammed Ben Bozid, sir, who shared his valuable experience on the topic put forward before him with ample instances. I also beseech his presence again to the institution for the benefit of all the members present over here. Sir, we are always ready to welcome your blessed session with the heartiest applause. Thank you so much, sir, for giving your valuable time and sharing such an informative session. Thank you, sir.
Thank you so much. Thank you for inviting me.
So, hello.
Hello.
So, I would like to give official vote of thanks. So, good afternoon, everyone. It is a matter of privilege for me to give vote of thanks in the 3-day quality improvement program for engineering and technology fraternity on second day. So it is for the information of our honorable speaker. The program was started yesterday from 11 a.m. onwards, and the chief guest of the program was Professor Ashan Singh, Honorable IEEE India Council Chair. Yesterday, Professor Bernie, IEEE Student Activity Program Chair, has given an expert talk on digital humanities, how to use EE and CS skills to solve mysteries in the humanities. All the dignitaries were welcomed by our Honorable Director, Professor Bhavesh Kumar Chauhan, and vote of thanks was delivered by HOD respected Professor Rafiq Ahmed. After successful completion of the first day program, today we have Professor Mohammed Ben Bozid, Honorable IEEE Fellow, IET Fellow, and eminent professor in Brest University. The topic of today's webinar is fault diagnosis and fault resilient control of electromechanical systems, tidal stream turbine case studies. Again, it is a great research topic and have an interest of many researchers in the national as well as international level. It is a privilege for me to appreciate our honorable speaker, Professor Mohammed Ben Bozid, who has delivered again his presentation in the efficient way. My sincere thanks and gratitude to our honorable eminent speaker, Professor Mohammed Ben Bozid, who has accepted again our invitation gladly and given us his valuable time. He has guided, motivated, and encouraged us towards recent researches in the field of fault diagnosis and fault resilience control for electromechanical systems. Honorable Sir, your contribution towards humanity is highly appreciated, and especially for condition monitoring of electromechanical systems. Once again, thank you very much, sir. I extend my sincere thanks and gratitude to our Honorable Director, Professor Bhavesh Kumar Chauhan, for his continuous motivation for organizing this kind of events, and also for suggesting novel topics of the interest of great participants. Sir, Department of Electrical Engineering and Electrical and Electronics Engineering are enlightening with your great experience and guidance. I also would like to thank to our respected HOD and convener of this program, Professor Rafiq Ahmed, for his time-to-time continuous suggestions and for moral support. Sir, we are unable to organize this kind of events without your continuous support. Lastly, thanks to all participants for joining the program. Hopefully, today's session will also be benefited to you all. Thanks IEEE BBDNITM Student Branch for organizing such an excellent program with the honorable reputed speaker. Thank you very much.
Thank you very much for your kind words. And I will be always welcome to make other presentation gladly. Thank you very much.
Yes, sir. Yes, sir. Thank you very much, sir. Thank you very much, sir.
Thank you.
Thank you very much, sir.
Thank you very much. Okay.
Thank you very much.
Okay. Bye bye.
All the feedback forms and other things are actually sent to your respective email IDs.
Okay.
If there is another questions regarding the things, you can ask.
Okay, program. Okay, all the questions have been discussed, Srikant. Thank you very much, honorable sir.
Thank you very much, and hope to see you in another possibility. Thank you very much.
Absolutely, sir. Absolutely.
Okay. Bye bye. Thanks. Bye.